Hey guys, what's up? My name is Mohit Kaushik and I'm studying in ICC College from College of Engineering and I belong to ECE branch. So today's technical seminar topic is physiological motion sensing via channel state information in next G millimeter wave communication systems. So moving on to the topic, these are the contents of our topic. First one is introduction, followed by history of technology, working principle, methodology, then results, then application, then conclusion, and at the last, references. So, wireless communication systems provide a channel state information. So, channel state information is the path between the receiving antenna and the transmitting antenna, which can be used to characterize the physical propagation environment. The small physiological motion of human subjects in that environment, such that associated with respiration, can modulate the CSI, thus allowing wireless physiological sensing through which a system presents even greater opportunities for wireless physiological sensing due to the advantages of small wavelength and high directionality. This work introduces a comprehensive mathematical CSI model to accurately characterize physiological motion captured by the amplitude and phase of the CSI of a millimeter wave communication systems. The model allows for the interpretation of intricate CSI pattern variations to avoid aliasing error and has been validated with experiments involving both parametric measures conducted with a robotic mover and respiration rate movements for human subjects. So let's begin with the history of the technology. So the history of technology for millimeter wave communication systems is a fascinating journey that has been significant advancement over the years. There are some key milestones in this technological evolution. The first one is early research which took place between 1960s to 1980s. So the exploration of millimeter wave frequencies began in the 1960s and 1970s, primarily for military radar applications. Because in those days we had a lot of wars going on. So this was a type of communication that was used to control the missiles and all the radio stations around. Researchers started studying the feasibility of using wave frequencies for communication purpose due to their potential for high data rates. Second one is microwave point-to-point links, which took place between 1980s to 1990s. In the 1990s, millimeter wave technology gained traction for point-to-point communication links, such as microwave backhaul for communication telecommunications networks. These systems operate in frequencies around 30 to 300 GHz, offering higher data rates compared to lower frequency microwave links. Wireless LAN development 2000. The early 2000s saw the development of the Wireless Gigabit Alliance, which aimed to standardize millimeter wave technology for wireless local area networks. 5G and beyond, from 2010s to present. The deployment of 5G networks in the 2010s brought millimeter wave technology into mainstream commercial use for all the communication systems. Ongoing research and development focus on enhancing wave technology for 6G and beyond, exploring new frequency ideas and beamforming techniques and antenna technologies to improve performance and coverage. So this is a system overview of our technical seminar of our experiment. TX refers to the transmitting wave and RX refers to the receiving wave. So static path is created to pass the signal, and both this signals received from transmitter and receiving wave are passed on to up-down counter, which is it is at the rate of 28 gigahertz, and it is narrowed down to 2 gigahertz, and it is passed to USRP. So methodology. So let's discuss about the methodology behind this project. So there are two ways basically, and we are going to discuss here about the first way, periodic motion detection by CSI amplitude. So first step is data collection. So use hardware capable of measuring CSI, such as software-defined ratios or specialized devices. Set up the environment where motion detection will take place, ensuring good wireless signal strength and minimal interference. Then collect CSI data while periodic motions are performed, such as walking, gestures, or other activities of interest. Next one is pre-processing. Clean the collected CSI data by removing noise and artifacts, which can be done through filtering techniques or signal processing algorithms. Normalize the CSI amplitudes to account for variations in signals, strength, and distance between the transmitter and the receiver. The next one is feature extraction. Extract relevant features from the pre-processed CSI data that capture the characteristics of periodic motions. Common features for periodic motion detection may include amplitude variations, frequency components, and temporal patterns. Next one is classification. Utilize machine learning algorithms such as support vector machine, random forests, or deep learning models for classifications. Split the pre-processed data into training and testing sets to train the classification model. Next one is train the model using labeled data, where each sample is associated with a specific periodic motion or a periodic motion act. Evaluate the model's performance using the testing set to assess its accuracy in detecting periodic motion by its amplitude. So moving on to the next slide. The next step is application validation. Apply the trained classification model to new CSI data to detect and classify periodic motions in real time. Validate the results by comparing the predicted motions with ground truth or human observations. Fine-tune the model if necessary to improve its accuracy and robustness in different scenarios. Deployment. Implement the periodic motion detection use system in practical applications such as smartphones, healthcare monitoring, or security systems. Ensure scalability and efficiency of the system for real-world deployment, considering factors like computational resources and data transmission requirements. So, what are the results? Experiments for this study were conducted according to the Committee on Human Studies Protocol number 148084, was approved by the CHS of the University of Hawaii system. The subject was seated in the chair in the same position where the robotic mower was initially placed. Reference respiration data were collected using a wristphone Maxim Integrated Health Sensor Platform 2.0 HSP. This sensor platform includes multiple plateau plethysmography and accelerometer sensors. Accelerometer x-axis output was used to obtain a reference respiration signal. Three subjects were tested, each breathing at three different frequencies, which is 0.2 Hz, 0.4 Hz, and normal undirected breathing. The Pro Metronome app by EUM Lab, installed on a smartphone, provided a visual guide to assist subjects with maintaining a consistent respiration rate at 0.2 Hz and 0.4 Hz. Table 1 summarizes the human testing data. In all cases, respiration frequency was detected from CSI amplitude and CSI phase with an error of less than 10%. In trial 3 for subject 2, there were different frequencies identified by CSI amplitude and CSI phase. However, in this case, the reference measurement also indicated two clear frequencies. This is due to respiration rate by normal breathing. Applications. What are the various applications of this physiological motion sensing via next generator wave communication? The first one is healthcare monitoring. Second one is physical rehabilitation. Third one is fitness and sports tracking. Fourth one is security and access control. And fifth one is assistive technologies. A comprehensive, so moving on to the conclusion, a comprehensive examination was presented on the impact that a subject with small periodic motion placed in the path of millimeter wave communication system has on the amplitude on the phase of the system CSI. A mathematical channel model was developed and accurately characterizes a subject's periodic displacement, regardless of the relative strength of the static and dynamic paths. The model provides a clear means of discerning when aliasing is generated in the constellation pattern, allowing a reliable recovery of the actual periodic motion rate. The model was validated using both a mechanical mode to stimulate respiratory motion and with human subjects. Experiments showed that both mechanical mover and human respiration rate measurements could be obtained with 0.02 Hertz of resolution. So we have used around 6 papers for references. All the 6 papers were published in IEEE conferences. So that's all for today's guy. That's all for today, guys. Have a nice day. Bye bye. Take care.